Okay, so far we have seen the definition of Markov chain, and we have seen many examples, more than 10 examples, I think. Now, what we will do this time is we will actually start the theory of Markov chains. Having seen so many examples, this is a good time to start that. And as we discussed, Markov chain is a very broad generalization of an IID sequence, in the sense that it has some properties of the IID sequence, namely it forgets the past, conditional on past and present, it only remembers the present. And that makes it a very useful model in real life. And in order to use this in real life, we need a very good theory, and that is what we are going to start learning from today. What we will learn today would be extremely basic, but we'll slowly develop these basics towards more interesting stuff. Just quickly recall, a discrete parameter stochastic process Xm taking values in a countable state space S is called a time stationary or time homogeneous countable state space Markov chain with initial distribution A and transition probability matrix P if MC holds. That is, for all positive integer n and for all I naught up to in in S, the joint distribution of x naught to xn is given by this quantity here. Okay? So the joint distribution of x naught to xn for every positive integer n is basically specified by this initial distribution A and this transition matrix Eij in this fashion. Now, we decided that without loss of generality, we'll assume that S is the union of all the ranges of Xn. Now, this just means that if there is a state which is not taken by any of the random variables Xn, it's a completely redundant state. We'll just throw it away. Okay? So let's do that from now on. We don't even mention that we are doing it, but this is assumed all the time. These are going to be our states. Okay? Any element of in range of any Xn is going to be our state, nothing else. And from now on, we'll always just say Markov chain. It will always mean the time homogeneous or time stationary Markov chain. Let this be our convention. Okay, so we start with such a Markov chain on a countable state space S, initial distribution A, and a transition matrix P. Now we are going to compute what is called a two-step transition probability. We already know what are the one-step transition probabilities. They are these elements of this matrix P, namely the ith element is Pij, which is, if you know that Xn is equal to I, what is the conditional probability that Xn plus 1 equal to J? And instead of Xn plus 1, now we are going to go to Xn plus 2. In other words, we'll fix two states, I and G in S, and since I is in S, which we have assumed to be the union of the ranges of Xn, as n runs over all non-negative integers, we can definitely find one non-negative integer n, at least one, such that I belongs to range of Xn. So fix such an n for now. Now, I is in the range of Xn is same as saying the probability of Xn equal to I is positive. Okay? Which means the conditional probability of Xn plus 2 equal to J given Xn equal to I is well defined. We want to compute this. As we will see, because of time stationarity of the Markov chain, this conditional probability is not going to depend on the choice of n as long as I belongs to range of xn, so that this conditional probability is well defined. As long as it is well defined, it's free of n, and this is what we will call the two-step transition probability from I to j. Now, our first goal is to compute this two-step transition probability from the definition of a Markov chain. Okay, so we fix I and j in S, and we get an n such that probability of xn equal to I is positive, so that the two-step conditional probability is well defined. So the two-step conditional probability is given by this ratio. It's well defined because of our choice of n. Now, let's first compute the denominator. We've actually computed this earlier when we are proving that MC implies MP. Okay? So let's do it again. This is the marginal probability of xn. Now note that in the definition of Markov chain, you only know the joint distributions starting from x0 to xn. So let's write it down in terms of the joint distributions. You just have to sum up all values of x0 to xn minus 1. And then that will give you the marginal distribution of xn. So this is the sum of I0 to in minus 1. All of them are in S, such that this joint probability. Okay. Now this joint probability is obtained from the definition of Markov chain as this quantity here. So therefore, the denominator of xn equal to I is this quantity. This is something we have already seen before. Okay, now let's compute the numerator. Now what is the numerator? The numerator, in order to compute the numerator, we have to go from x0 all the way up to xn plus 2, the joint distributions, and then sum over all possible values of x0, x1 up to xn minus 1 and xn plus 1. Okay. That will give me the joint distribution of xn and xn plus 2. Except these two random variables, everything else has to be summed up. So that's precisely what we have done here. So we have computed the joint distribution of x0 to xn minus 1, xn, then xn plus 1 and xn plus 2, and then summed over all possible values of x0 to xn minus 1, that's these sums, and then also all possible values of xn plus 1. So that will leave us with the joint distribution of xn and xn plus 2. Now this, of course, can be written from the definition of Markov chain in terms of the initial distribution of the transition probabilities. That's what we have done here. Okay, we just wrote it longhand. All the transition probabilities are exactly as we need from this previous step. So note that we have n many sums here, starting from I0 to in minus 1, and then we have a sum, extra sum of k over k in the numerator. On the other hand, in the denominator, we have n many sums, which are exactly same as the first n many sums here. Okay. So let's summarize this, whatever we said. So the conditional probability is just this ratio, and this is well defined because of our choice of n. Now we'll just put the values of numerator and denominator. Denominator exactly what we had, and numerator is also exactly what we had in the previous slide. Except that here, okay, it's the same thing, except I have used a different color. Here, I'm stressing that this sum is not there in the denominator. And similarly, this particular this part, these two quantities are not there in this sum in the denominator, except that everything are the same. Okay. So I'm stressing by a different color. Now note that just like in the proof of MC implies MP, note that this part has nothing to do with these guys here. So in other words, all of these can come out of this sum here, and this can go here. So that will give us this equality over here. I've just used the fact that all these guys have no k in it, so it can come out of this sum. And similarly, this has no I naught up to I n minus 1 in it. So that's a separate sum. So this becomes a product of two separate sums. And the advantage is that now the first quantity here is the same as this denominator. And the denominator is positive by our assumption, so it can get cancelled. So this will get cancelled, only the rate part will remain. Now note that this quantity does not depend on the choice of n. As long as this is well defined, this equation is true. This is equal to this thing. So this is what we'll denote by P2ij, and this would be called the two-step transition probability from I to j.